Okay, and the second part of the question is to calculate the lattice enthalpy. Now this may be a term that you're unfamiliar with. In chemistry, especially early on in high school, we talk about metals losing electrons to either get a full outer shell and sometimes to become happy or something like that, or chlorine wanting to gain electrons to get a full outer shell and to become more stable. And teachers may even talk about them being lower in energy. And there's some truth to that. But it does actually take energy for this to happen. We have to put in energy to turn sodium into sodium plus as an ion, the first ionization energy, and it does take energy for chlorine to gain an electron. And these are energy intensive kind of processes in a way, but the result is a solid which is much lower in energy because of the attraction between the cations and anions that hold it together, and this overall lowering of energy is makes it stable and kind of drives this process, but we do have to put energy to this for this to happen. Now lattice enthalpy is the energy that it takes to change it from a solid back into a gas, so we're kind of doing the reverse of this process of forming a solid, and we can usually calculate that out, but it's not usually done directly. It's usually done by having other information, and that's what we're going to try and do now. Now if we look at the question, this is what we're trying to figure out. We're trying to go from solid sodium chloride to produce sodium positive ions and the anions, the chloride ions. And you should kind of get the feeling when we're looking at this that really this is just going to be one of those ones where we're going to write out some equations, we're going to manipulate them in terms of either reversing them or combining them, and through a process of perhaps cancelling, we're going to end up basically forming this equation that we've got at the top here. So it's going to be helpful for us to write out the equations for the different bits of information that we've been given to see which ones are useful, and then we're going to manipulate them to try and work this problem out. Now, an important equation to remember is the one just that we did previously, which I've just rewritten there, which is the sodium and chlorine going to sodium ion and chloride ion, which was 147 kilojoules. That's going to be handy. Now, what I've done is rewrite these equations here and just to show you what they look like. Now it's important just to take care with them, make sure you're checking that sodium, it's not sodium chloride, that this reaction here is the enthalpy of formation for sodium chloride. So obviously if we want sodium chloride to be as a solid on the left, we have to reverse that equation, so you just need to take care with things like that. Now here's some of the equations written. The first one was the formation one, which I've just reversed, and the vaporization one, sodium going from a liquid to a gas, and the fusion one for sodium going from a solid to a liquid, the ionization energy one, and the bond enthalpy one where we're just breaking that covalent bond and we're going to get two chlorine gas atoms, and the electron affinity one, which from the previous question the information given should have made it possible to work out. Now we have to arrange these to try and get this equation at the top, and that's really just a little bit of algebraic manipulation. Now I've just numbered the different bits of information we've got for enthalpy here for the equations that I'll be using from 1 to 6, and I'll be rewriting those to show you how we're going to do the calculation. Okay, now this is the equation we're trying to work out at the top. Sodium chloride going to sodium gas ion and the chloride ion, the sodium positive ion. Now the formation equation I've put there, but the other important one we're going to have is the one that we used from the previous question, which is the sodium gas plus Cl gas going to, because of course we get the ions on the right hand side, which is what we want. So Now, if we look at that, obviously the first thing we see is we've got a Cl2 here and a Cl here. So the natural equation to write is the following. Now this equation is the bond enthalpy one, and obviously we only need half of a Cl2, so we just have to write half in front of that, and remember that when we, and that's obviously going to change from that to being a 1, and when we actually comes time to do our calculation, that's going to be, so we just actually get rid of the 1 as well. It's going to change just being half of that numerical value. So that's going to get rid of that as well, so it's going to cancel that, and it's going to also cancel that. Remembering on opposite sides we cancel, and on the same side we add. Okay. Now the next equation is going to be obviously we want to get rid of the solid sodium chloride here, and that's going to go from being so we want to have it on this side, and it's going to go to a liquid, and that's going to be the equation number 3 up above, which is just the fusion one, and we also want this to end up being a gas, so it can cancel out completely, and that's going to be this one here. Okay. Now just pointing out a little mistake I made, that shouldn't have an ionic charge here, so I'm just going to get rid of that there. That should have been just a gas. So that means that we've got this solid here is going to cancel with that solid there. This liquid here cancels with this liquid there, and that gas there cancels with that gas there, and that really leaves us with what we want, which is just going to be sodium chloride going to the sodium ion and the chloride ion as gases. Now if we add up those, remembering to take account of the half and the fact that we reversed one of the equations up here, we should get our answer. Okay, and if we add those up, we get the plus 411 from this first equation up here. We get the 147 from the previous question where we figured that out. We're halving this one, which is this amount here, and just adding up these two, the 2.6 and 104, that gives us 785.6 kilojoules per mole. So if you kept your head and did all your calculations and your manipulation of these equations properly, you should be okay on that one.